Alright, so in this video we're going to take a big look at resonance and damping. So this task was done in conjunction with a practical measuring the resonant frequency of a system, but that's not too important for the rest of it. So the first thing to know is the practical was centered around a system which had a 100-gram mass and a spring with spring constant 25 newtons per meter. So the first thing to do is work out what frequency would cause resonance, so what the natural frequency would be. So we can do that. So frequency is 1 over 2 pi square root of k over m. So it's going to be 1 over 2 pi square root of 25 over 0.1, which is going to be 25 divided by 0.1 is going to be 250. Square rooted divided by 2 divided by pi. This is 2.5 hertz. So essentially this system is going to resonate at multiples of this 2.5 hertz. So 2.5, 5, like 10, 20, whatever. The next part was essentially testing this. So with the system, I think most people, when they did this, actually managed to find a very good resonant frequency around about 30 hertz, which is one of the harmonics of this, the natural frequency. So you'd expect resonance to occur at that point. Let's not worry too much about that. Okay, so describe the energy transfer occurring during horizontal mass spring system oscillation. So we've got mass spring. If it's in horizontal, it's essentially you're going to be exchanging elastic potential energy with kinetic energy. So let's start with elastic potential energy. So if that's the starting point, halfway through it would have all been converted to kinetic energy, and then onto the other side it would go back to elastic potential energy. So we're now halfway through a cycle here. So if we imagine our system, I don't know, you have something like a bit like this. Essentially what's going to happen is you'd initially displace it to the left, so it would come back through. So if we displace it to here, it has elastic potential energy, go through here, it would have kinetic energy, elastic potential energy, come back, kinetic energy, elastic potential energy. So during one full oscillation, you'd essentially have elastic potential energy halfway through, and then at each end of the oscillation, and in between those some kinetic energy. Explain the difference between a horizontal mass spring oscillation and a vertical in terms of energy. So in vertical, you have to consider GP. Ooh. So in vertical, it still starts with elastic potential energy. So this is the point it would have maximum elastic potential energy. That would be transferred into kinetic energy. And then if it's going upwards, it would also gain some GPE. And then that would all be transferred into maximum GPE at the top. This would be then converted back into kinetic energy, and then like some GPE still, because it hasn't reached its lowest position, and then back to EPE max. So essentially, this is the energy it has at different points in the cycle in a vertical, and in horizontal it doesn't have these GPE terms there. All right. So what happens to the amplitude of a vibration over time? So in terms of describing the amplitude decays to 0. So what do I mean by that? If we plotted a graph of the amplitude against time, so we initially displaced it, what we would get is a graph that looks a bit like this. And the reason for that is some work is going to be done against air resistance. So essentially some of the energy it could have in terms of GP or kinetic energy or whatever is transferred to work. So essentially your system is transferring energy to the surroundings at all times. All right, so let's continue with this. So this is what I was talking about just now. So this is like about explaining why. So work done against air resistance. And what that means is that went a bit crazy. The energy is transferred. This isn't writing too well today. Anyway, energy is transferred to the surroundings, and it will be in the form of thermal energy or like heat, if you like. So that's what's going on. That's why your energy is decreasing over time. If in each oscillation the system loses 10% of its energy, calculate the final amplitude after 10 oscillations if the initial amplitude is 20 centimeters. So essentially, the energy after 10 oscillations will have been multiplied by 0.9 to the 10, because that represents losing 10% of its energy each cycle. Now, energy is proportional to amplitude squared, which means that the amplitude has been multiplied by square root of 0.9 to the 10. The reason for that, so if amplitude squared overall gives you a change of 0.9 to the 10, each of the amplitudes must be multiplied by square root 0.9 to the 10. So what we're going to do is we take 20 centimeters times by 0, times by the square root of 0.9 to the power of 10. And if we do that, we'll get a amplitude of it's like 11.8. So it was 20 centimeters times by the square root of 0.9 to the 10. 20, which is 12 centimeters to two significant figures there. The key to this being this relationship here. So there's, and the reason for that is if you've got like a mass spring system, the energy is obviously stored in the form of elastic potential energy, and when it's at its amplitude, all of the energy will be elastic potential energy. So you can see here, that's why you get the energy is proportional to a squared term. All right. All right, so let's have a look at some multiple choice questions to do with this. So we've got a periodic force being applied to a lightly damped object, and they've got a graph of amplitude against frequency. So what we can see from this graph is we've got a resonant peak here. So this must be the natural frequency or the harmonic of the natural frequency of the system. So what best describes what would happen to the shape of the curve if damping had been greater? So damping causes the amplitude at all points to be lower, so it would kind of look like this. So what we're looking at is answer A. It's certainly, if you increase damping, the amplitude is not going to be greater, so we can get rid of that one. It affects all of the graph, so it's not just certain sections, so those two are wrong, so it definitely was A. Okay, so we've got an oscillatory system subject to damping is set into vibration by a periodic driving force. These graphs are all the same scale, show, like essentially we need to work out which one has the lightest damping. So we can already eliminate this one because it's got like the lowest, and this one because they've got the smallest resonant peaks essentially. So like the difference between these two is much smaller, so we know it's not those two. The key here is to recognize that for these graphs, essentially these keep going on like this. So you can see on this one, the rate of increase is actually very small, so the resonance is actually being damped. We've got a much, whereas on this one here, we can see we've got a much steeper gradient indicating lighter damping. So the correct answer is this one here. And you can see this graph of A here is essentially showing like a middle section in here. So we can see on this graph, the gradient is steeper for a peak, which indicates lighter damping. Okay. Okay, so which one of the following statements applies to a damping force acting on a vibrating system? So it acts in the same direction as acceleration. No, it doesn't. It always acts against the velocity. So therefore it's not B. So essentially damping always opposes the velocity of the object. So it's answer C. And no, it's nothing to do with the displacement. It's only to do with the velocity. So let's scroll down. Let's zoom out so we can see both of these. Okay, so which one of the following statements about an oscillating mechanical system at resonance when it oscillates at constant amplitude is not correct? So asking, so the amplitude of oscillations depends on the amount of damping. What it does, so that this statement here is true, so that's not the wrong one. The frequency of the applied force is the same as the natural frequency of oscillation of the system. It's at resonance, so yes, absolutely, that's true. The total energy of a system is constant. If there's no damping, and like obviously total energy is always constant, that's just conservation of energy, so that one's true. So the applied force prevents the amplitude from coming too large. No damping prevents the amplitude coming too large, so that's the statement that is wrong. Which one of the following statements concerning force vibrations and resonance is correct? So an oscillating body that is not resonating will return to its natural frequency when the forcing vibration is removed. Yes, because once it's in free vibration, not forced vibration, it will vibrate at the natural frequency. So that one is true. So let's just check all the others are wrong. At resonance, the displacement is 180 degrees out of phase. No, it's not. It's 90 or pi over 2. That one's wrong. A pendulum with a dense bob is more heavily damped than one with a less dense bob of the same size. No, it isn't. Damping force is proportional to surface area. The density would have no effect. Resonance can only occur in mechanical systems. No, there's loads of other types of resonance, so that's absolutely not true. It doesn't have to be mechanical, like sound, for you can get resonance, for instance. So we know that it's A, so having got rid of all of those. All right, so that concludes this video.